My name is Tomasz Puzyn. I'm professor of chemistry at the University of Gdansk, and in parallel, I'm CEO of QSAR Lab, which is a spin-off company under the umbrella of the University of Gdansk. And it's my pleasure to be here, and at this moment, I would like to express my great thanks to the organizers for inviting me, as I'm acting as an external speaker. So I will be talking about merging two methodologies. QSAR stands for quantitative structure-activity relationship for nanomaterials, and Nano-AOP, adverse outcome pathways. In my presentation, in the first part of my presentation, I will introduce you the general idea of how to do that with using omics data as an interface. This idea will be illustrated in the second part of my presentation by a kind of proof of the concept based on one pathway and one group of multi-walled carbon nanotubes and AOP 173. You probably know what is QSAR and what is the general idea standing behind. Just briefly summarizing for those who don't know. When we have a group of more or less similar nanoparticles, and we have a variation in the structure of these nanoparticles, we can correlate the variance in the structure with the variance in the activity. So the variance in the structure is usually represented by a set of structural features. We call it descriptors. And in case of nanoparticles, as Mark said, previously, it's a very complicated issue. So I'm not going to go, deeply into details. So just to give you a flavor, this can be size, shape, coating, structural functionalization, system-dependent behavior, as well as important descriptor of physical properties of and structure-related features of nanoparticles. And this can be related to the variance in the activity. And usually the variance, and when we are developing QSAR, we are using phenotypic toxicity endpoint. What does it mean? For instance, we are developing QSAR for in vitro cell viability, for in vitro cell death, for mutagenicity, acute toxicity, different types of ecotoxicity, for instance, and organ toxicity. So we are observing phenotypic toxicity endpoints, and we are trying to see how the for instance, cell viability or other endpoints are changing with changing structure of our nanoparticles in the group. On the other hand, we have AOPs, and the answer we can get from AOP is that how a given nanoparticle, given type of nanoparticle, initiates the cascade of key events, causatively related key events that result in the adverse outcome. Usually, this nanoparticle should interact with something in a cell. So the presence of a given nanoparticle causes the chain of or the network of key events. Yes, but why not to ask a question? Is it possible to merge these two, issues? Yes, because in case of QSAR, we are mainly focusing on the chemistry. So how chemistry of nanoparticles, how different types of, coating, functional groups are related to the biology, but we are not going very deeply into biology. On the other hand, when we are developing AOPs, we are focusing on biology. We are thinking how to relate different biological events and what is the causative relationship between different biological events. Our hypothesis was to merge methodology for searching or for exploring the information on chemistry with the methodology for exploring the information on the mechanism, on the biological mechanism of toxicity. We think, in our opinion, the omics data, especially transcriptomics data, can serve as a kind of an interface between chemistry and biology. You have chemistry described by different descriptors, and biology described by AOPs. And according to our knowledge, there was no such kind of merging before. In many QSAR models, people were tried to use omics data as descriptors, as additional descriptors related to the structural features of nanoparticles to predict AOPs. Yes, but we think we tried to do the opposite thing. So we identified and we postulate that this is a method of linking these two methodologies. We postulate that for early key event we can identify relevant transcriptomic endpoints at omics level, molecular levels, and then we tried to correlate the variance in the structure to the variance in the initiating the AOPs. So this was the idea, and now I'm going to show you an example how we tried to verify this, if this is feasible way of merging or not. So we were working with data for 10 multi-walled carbon nanotubes, and for these 10 multi-walled carbon nanotubes, we collected 7 very simple descriptors like length, diameter, aspect ratio, defined as 1 divided by another one, length by diameter, surface, carbon purity, and information on functionalization. And we also collected transcriptomic response expressed in terms of BMDL values for various pathways relevant for AOP 173. You have already heard from Sabina Halapanavar about this very important AOP, one of the 5 developed under SmartNanoTox and already accepted by OECD. And we tried to correlate the structural variance of these 10 multi-walled carbon nanotubes with the BMDL values for pathways which can be important for early key events in this AOP. So just to be clear, BMDL is the statistical lower bound of the estimated benchmark dose, BMD. And this we can assume that this is the dose at which we have no observable effect levels, so no observable effect. So this means that this is the higher dose at which the AOP is not induced. We started from data from BMDL values that we had for 20 different pathways, and we applied 3 filters to select one pathway to be studied later on and to be used as for modeling as the proof of the concept. So we were trying to select, pathways with the lowest BMD values, so means that at the lowest values the activation occurs. Pathways associated, of course, with the early key events of AOP 173, and pathways consistently perturbed across 10 multi-volt carbon nanotubes. So by applying those filters, we selected three pathways, and we measured determination coefficient, which is a squared correlation coefficient with the seven descriptors, and we selected finally the agranulocyte adhesion and diapedesis pathway, which was very highly correlated with the aspect ratio. So we started, developing the model, and the dependent variable was, of course, BMDL value for this agranulocyte and adhesion and the diapedesis pathway. On the other hand, we had a set of 7 predictors, but the highly correlated aspect ratio was finally taken to the model, and we divided our set of carbon nanotubes into 2 sets: training set used for calibrating the model, and validation set used for validating the model. Our set was very small, so we used only three carbon nanotubes as validation set, but to avoid the problem related to that the fact that the statistics can be related very closely to the splitting procedure. So, for instance, which carbon nanotubes are used for training, which for validation, we perform multiple splitting procedures. So we split our data 4 times into different training and validation set, and we obtained 4 different models, as you can see here, with calibration parameters, cross-validation parameters, leave one out, and an external validation parameters here. Here are the determination coefficients and validation coefficients for the external validation set. Should be as close to 1 as possible. And here we have root mean square error of calibration, for the error for the calibration set, and for the validation set here. So we obtained 4 models. So finally we have calculated the so-called consensus model, which is a kind of average model, to make the model as much independent on the splitting procedure as possible. So in this model, it had quite good calibration and validation parameters. And when you look at this equation here, we can see that when the kappa value, the aspect ratio, is increasing, the BMDL value is decreasing. So this means that highest aspect ratio, highest toxicity. Yes, because lower BMDL means higher toxicity. So this was the first part. Yes, and in this part we related the structure of our nanoparticles, the aspect ratio, to the strength, let's say, of the activation of the agranulocyte adhesion and diapedesis pathway. In the second part, we used, this relationship to perform an attempt of grouping based on, based on this. So according to all recommendations, grouping should not be performed only based on the structural similarities, but these structural similarities should be, of course, related to their toxicity. So we need to know which structural features are important for its toxicity. And to make that, we perform principal component analysis, and additionally, we colored the points, our carbon nanotubes here, in the scale, color scale, with the color scale related to the kappa values, so to the aspect ratio. So in effect, we obtained two principal components, explaining together more than 50% of the total variance in the data. And as you can see, the first principal component here, the x axis here, was mainly related to the expression of cytokines and chemokines relevant for the inflammatory process. But interestingly, the second principal component was mainly related to myosins and selectin here. And by the way, when you see the arrow up, means that this particular gene was upregulated by those carbon nanotubes having high values of PC2, and downregulated when you see the arrow down. For instance, selectin in this case was downregulated and myosins was upregulated, and on the opposite side, selectin was upregulated by those carbon nanotubes, and myosin was downregulated here. So, interestingly, we were able to observe that the second principal component divided our carbon nanotubes into two groups. The first group, we call it high aspect ratio multi-walled carbon nanotubes, were located here with positive values of PC2, and those entangled or low aspect ratio multi-walled carbon nanotubes were located here with having negative values of PC2. So, this is a very interesting observation, showing that there is different mechanism of action. Yes, that a high aspect ratio multi-walled carbon nanotubes upregulate those genes and downregulate those genes, and low aspect ratio entangled multi-walled carbon nanotubes upregulated these genes and downregulated these genes. And of course, we were able to develop another QSAR model which related the value of PC2 to the kappa value. Yes, and this model, which can be easily used for classifying new carbon nanotubes, either into a group of high aspect ratio and acting according to this mechanism, so activating this, upregulating this, downregulating these genes, or to a group of entangled multi-walled carbon nanotubes, downregulating these genes and upregulating these genes. And when you calculate the average threshold, is about as I remember, is about 68. The kappa value is 68. So this is the threshold. Above is group 1. Below is group 2. In addition, when we look at group 1, we can see group 1A and 1B, and this group 1A and 1B are differing by the induction of different pro-inflammatory genes. So these two genes are mechanism is related to first and second key events in the AOP, and would help us to identify and define better molecular initiating event. What is happening? Yes, because for instance, as we look here, L-selectin is an adhesion molecule expressed on most of leukocytes and regulate accumulation and activation on neutrophils and monocytes in the sites of injury and inflammation. And if we have high aspect ratio of multi-walled carbon nanotubes that don't regulate cell, as they may competitively bind to the ligands required for activation of selectin and inhibit their interaction, which in turn might impact activation of agranulocyte and their the diapedesis process. So we can, we are able to better explain what's going on, what is the molecular initiating event, in this case. Similarly, when we look at myosins, the expression of myosins was largely altered following the expression to long nanotubes, which may suggest that long nanotubes affect the cytoskeleton arrangement, impeding the diapedesis process. And similar differences are found in the expression of several cytokines and chemokines that signal and coordinate the diapedesis process. So in summary, when nano-QSAR models are based on only phenotypic data, molecular mechanisms remain unclear. When developing nano-QSAR, one can only conclude that the presence of a given type of nanoparticle initiates the AOP. And when you integrate both methodologies, the omics response can serve as the interface. And the integration helps explaining the influence on the structural variation of nanoparticles, differences in chemistry, on the variation of AOPs, induction, and differences in biology. The only problem we had was how to develop a new acronym for the integrated methodology. Maybe you can help and suggest maybe something else. So with this moment, I would like to thank Sabina, Andrew, and Ula, and Carolina and Anna from my lab, that they were involved, all were involved in the developing of the proof of the concept I demonstrated to you in the second part. So thank you for your attention, and I will be very happy to answer your question.